Let's talk about slew rate in power amplifiers. And here is a very accurate comment about the slew rate. I'll read it out. At the 42nd minute there was a telling moment, and what had been hidden became obvious. The commentator asked, one expert read it, the second answered, and it seems that none of the three of them knows the unit of measurement for the slew rate of the output voltage. I'm not saying anything about the commentator, and a priori he might not know, but the two experts just let it slide out of misplaced tolerance. Oh, guys, it's all wrong, guys. These aren't the first comments about slew rate, and maybe we should take a closer look at this issue, including the theory. Yeah, I know nobody cares about theory, but if we don't look at the theory, the discussion ends up being really superficial. But if we go through the theory, then look at the calculations, then look at a specific circuit, and also see how this is achieved and how difficult it actually is, then a lot of things will fall into place. So what does the slew rate describe? Here we have an operational amplifier, and if we apply an ideal signal with an instantaneous slew rate at the input, well, in practice that's impossible, but a very fast one, faster than this operational amplifier can handle. Then it will respond with a delay, so it can't reproduce this pulse perfectly. You see, there's this kind of slope, and there's a delay time before it reaches the maximum level. It's the same definition, but here it's more scientific. So we measure from 10% because the starting point can be different depending on the device, up to 90%. Basically, this is considered an accurate measurement. The time it takes for our signal to go from 10% to 90% is considered the rise time. Let me read the definition. You can think of slew rate as the maximum rate of change of the amplifier's output voltage. This value is crucial in electronics because it determines how well your circuit handles rapid changes in the signal. When you work with high-speed, fast signals, choosing a component with an appropriate slew rate helps avoid issues like distortion or unwanted noise. For example, in video or radio frequency communication systems, a higher slew rate allows the amplifier to keep up with rapid changes in the output signal, but if it's too high, it can lead to instability or additional noise. In general, the slew rate is also related to the bandwidth. If the bandwidth is larger, we have more noise. So there is a reasonable limit that we work with. It doesn't mean that more is better. And here is the continuation. The slew rate can be defined as the maximum rate of change of the output voltage of the amplifier. When you apply a rapidly changing signal, the amplifier is not always able to keep up with it. The slew rate shows how quickly the output can respond. If the signal changes faster than the amplifier's slew rate allows, the output signal will not match the input. Well, we saw that. The operational amplifier did not reproduce the original shape. This can cause the signal to appear distorted or lose important details. And why is the slew rate important? This issue is particularly evident in audio systems. For example, if you're trying to play a high-frequency sound at a high volume, the amplifier might not be able to handle it. As a result, the shape of the output signal can become compressed or even change, turning from a smooth sine wave into a triangular one. Such changes add unwanted harmonics and reduce the sound quality. And here is an example or a note. In audio amplifiers, a sinusoidal signal with a frequency of 20 kHz and a peak-to-peak amplitude of 56 volts, not RMS but peak-to-peak, which is typical for a 100-watt amplifier on an 8-ohm load, requires a minimum slew rate of about 7 volts per microsecond. Remember this number. This is the minimum. Many amplifiers are not capable of reaching such speed, especially at high power, so when the system is overloaded, audible distortions may occur. Well, today I would say semiconductors are so good that, in principle, most of them can meet these requirements. And let's take another look at the physics behind this diagram. Let's imagine that here we have, let's say, a low-power amplifier with a 10-volt output. It reaches this with that slope. But what if it needs to reach 100 volts? Okay, well, I can't fit that in here. Well, let's do it twice. 20 volts, right? So, in the same amount of time, it has to go through a steeper one. This slope keeps changing all the time. I'll try to draw it. Let's put it this way. We need to reach a signal that's twice as big. Yeah, somewhere around here. And we end up in the same amount of time. This is our time here, right? And from here it needs to get there. Well, you see the slope is much, much steeper. If you have 500 watts there, it changes even more. Pretty cool, right? That's why for a low-power amplifier it might be enough, but for a powerful one it should be bigger. Well, in this diagram, here's the input signal. See, it's perfect. It comes in instantly. This is the response of our amplifier. Well, in practice, no amplifier can react instantly, right? If you apply such a signal from a good signal generator, it will always be, well, close to ideal, but the response will be delayed. That's the whole point of slew rate. How many volts can it output in 1 microsecond? So we have a fixed amount of time. For example, 1 microsecond. And this value here, how much is it? 1 volt, 7 volts, 40 volts, and so on and so on. Well, how much do we actually need for a good amplifier, right? For a good one. And let's take, for example, a 500-watt amplifier. This is the perfect amplifier for home audio playback, when we're listening quietly, while still delivering the most accurate reproduction. 100 watts is not enough. It's not about volume. It's about accurate reproduction. And let's do it quickly. Let's calculate what our peak value is. Well, you can do it yourself. Well, basically 90 volts is our peak value that the signal should reach at full output power. Here is the formula for the slew rate for a sinusoidal signal. Here it is. Well, and our maximum frequency is 20 kilohertz, which we need to handle. With some headroom, let's say 30 to 50 kHz. That's basically how all amplifiers are designed, with some headroom built in. So what do we get? At 20 kilohertz, the required slew rate is 11 volts per microsecond. If it's lower, we won't be able to draw a sine wave. But at 30 kHz it's 16, and at 50 it's 28. Well, if we want a good amplifier like that, then 28, I would say at least. 28 volts per microsecond at minimum. But since we want the very best there, and in music, for example, even a piano or a grand piano is a percussion instrument. It's a percussion instrument, not just drums. We have many percussion instruments. And we want to reproduce the piano very well. Then the industry said that a good level there is 25 and a very good one is 140, 40, 60. So 40 volts per microsecond for a 500-watt amplifier is considered very good. And when we talk about what is needed there, we know that 40 or 50 is very good. If someone makes it even better and better, it doesn't make sense anymore. Yes, there is a parameter, but that's already overkill. Let's calculate the same thing for SPV, for an 8-ohm load, also for the most difficult case. Yes, let's do all the same calculations. What's its peak value? We get about 90 to 95 volts. The minimum required is 11.3 volts per microsecond. For 30 kHz, it's 17. For 50 kHz, it's 28. But if we want even better, then we need somewhere around 40 or 50. And basically, overall, for Class AB amplifiers, this is much more difficult than for Class D amplifiers, because a different amplification principle is used, right? This is pulse width modulation, and here we can implement everything much faster. That's why Class D amplifiers, as they say, deliver bass very well, and handle other things too. This is because the slew rate is easily achieved in Class D amplifiers. Very easily. Everything is limited only at the filter level. So, approximately, the ICE Power 1200 AS2 has about 40 or 50 volts per microsecond. But it has a special feature. It uses a bridged configuration. So in actual playback it gets doubled, because while one half of the sine wave goes up, the other goes down. So it goes at double speed. The Ice Power 1200 AS2 has a slew rate close to 100 volts per microsecond on the rising and falling edges. If you look at the output, because it's built in a bridged configuration, it means both arms move away from each other very quickly. If you look back at this picture here, you see that Ice Power has the midpoint here, and one arm goes up while the other goes down. This makes it much faster. With the half-bridge circuit, we start from zero, right? We start from zero. And how does this show up for clients? Many clients have good brand name amps. Their amplifiers are within 100 to 150 watts. Well, almost all of them. And of course their slew rate is lower because of this, and they don't control the woofers as well. And when they connect a machine like this, where all the parameters are off the charts and there's enough power, the bass starts to come through very clearly. Control and a very clear initial attack, and it starts to work surprisingly accurately. And just recently one client of mine bought an amplifier, and he says how well it delivers the bass when I listen at low volume. It's all because of this. Because this architecture is very good. Well, so, here is a kind of generalization. And what does the literature say? It says that in Class AB it's harder to achieve this. It's possible, but much more difficult. And in principle, there are various hidden distortions present there. But for Class D, since it uses a different principle, the rise and fall times are very fast. This is very easy to accomplish. There are practically no classic slew limitations. It's mainly limited by filters and the modulator frequency. In the future, these modulators will likely improve further. Today, though, we're already far beyond the usual parameters. And let's see how this is implemented in practice in this unit. Why all of this works out so well. Well, like that. Here we have a module. And to achieve this slew rate, it means we have 4 channels here. You see 4 gate drivers for the FETs. Yes. These channels at the development stage are connected in a bridge configuration. And here, on a single ferrite ring, there are 2 coils. Yes, it's made very neatly here. Otherwise, there would have to be 4 here. They handled everything very efficiently. Well, the design is really on the verge of science fiction. And to achieve all this speed, look at how the architecture is made. So here we have... The subtitles were made by the phase corrector filter. There's a large inductance here. And this whole system, altogether, pumps up to 400 volts. So there are small currents at the front. And there's still no large input capacitor, because these capacitors, electrolytics at high voltages, are a weak point, and usually the lifespan of such devices is no more than 10 years. But if you design the architecture differently, like here there's a film capacitor, then all the accumulation happens here. The energy is stored here. And everything that needs to be boosted we temporarily take from the coil, and of course from the power grid. But all the peak power we take from this PFC, which has a very high voltage, about 400 volts. Then it gets boosted through this ferrite transformer at high frequencies. In terms of size, it can handle about 5 kilowatts, but there are few windings here. That's it. All of this, the whole design is made so that there are minimal losses everywhere. And then here we have the main storage units. Yes. This is where the energy is stored for our slew rate. Because the power, or the instantaneous power demand that comes from a drum hit, no circuit, no large toroidal transformer, no one can deliver that. That's why we have a storage bank, and it immediately fires off those first volts. And because these large storage units have relatively higher internal resistance and a certain amount of inductance, so overall it's also a bit slow, and that's why it's duplicated with these small parallel capacitors, so that initial demand can be supplied immediately. And then we get a bridge circuit with instant delivery of the stored energy, which is quickly supplied to these MOSFETs. They're on the other side, down below. Well, you can barely see them there, but you see one is visible on the left, right here. There are 8 of them in total. And it turns out that it just delivers that slew rate with basically no limitation. The only limitation we have is with the filters, so the bandwidth is about 50 kilohertz kHz. Well, that's pretty much standard for these designs. Because it's a bridge type, it doubles, so we get close to 100 volts per microsecond. And that's why it's so lively, yeah. This unit is so lively. And right away, when my customers, especially now thanks to Premium Hi-Fi, recognize me in Latvia more and more. Well, probably because people my age or clients of that age don't always speak English very well. That's how people have always bought from me. Around the world, like Europe and developed countries. But with Premium Hi-Fi, I found different clients. I get customers from Latvia too. I get more feedback. I give them products for testing, and they test them. Oh my God, the last one took a week. He just stopped by on Saturday. I gave him a sample, and then on Saturday evening he calls me. That's it. He's already made all the decisions. He's selling everything he had, installing this one, and he's so happy and excited. He had such a strong argument. His wife wasn't interested in music, but when he showed her, she said, "It sounds really good." Well, as I understand it, this is something extraordinary. But overall, this unit alone almost solves the entire problem of power amplification. Next, we invest in speakers and a preamp. So even in terms of slew rate, we have confirmation of how good everything is. Well, I hope I answered the question about the slew rate, because you can't really explain it in simple terms. Here, you need to understand the theory, and then we all understand more or less the same thing that's meant by, well, in this kind of industry jargon or technical terminology. Sometimes when we use certain terminology, there are always physical processes behind that terminology, and that's important. And in conclusion, I want to express my gratitude to the viewer who leaves a very competent, very well-written comment, and we will try to respond to such well-formulated comments with short videos.